Okay, for the gravitation, okay, mm, let's see. There is a point drawing the centers of the mass of Jupiter and Ganymede at which the net gravitational field is zero. So what this means here is that there's a neutral point. Okay, so calculate the distance between this point and the center of mass. Now from this point, let's let this point be the neutral point. Okay, we let it be x. Okay, this distance. So this distance will be 1.07 times 10 power 9 minus x. Okay, so the distance between Ganymede, no, this is a distance between them. So this is the where we want a neutral point. Okay, so for part A, neutral point means G mass of Jupiter divided by x square. Because you want, I let this distance be x because they want the distance between the point and Jupiter. So straight away you find solve for x, you'll get it. Okay, equals to G mass of Ganymede over 1.07 times 10 to the power of 9 minus x square. Okay, so the G cancels out on both sides. Now mass of Jupiter is given by 1.9 times 10 to the power of 27 kg, okay, times 1.07 times 10 power 9 minus x square. Okay, this is equals to let's see, where is the mass of Ganymede? 1.5 times 10 power 23 x square. Okay, so let's shift this a little bit. So what happens here is just some mathematics. We can just straight away remove this first, become 4, and remove this, so it makes it smaller and easier. Now the thing is, because x greater than 0 and 1.07 times 10 power 9 minus x is also greater than 0, it means both are positive. We can just square root both sides. Okay, square root of 1.9 times 10 power 4, 1.07 times 10 power 9 minus x square, without the square now, okay, equals 1, oops, uh, 1.5 x. Okay. Okay. So next we just need to uh do some basic mathematics. Let me just use my calculator. 1.9 times 10 power 4, then square root. So I just need to multiply by 1.07 times 10 power 9. I get, so these two multiply together, 1.4749 times 10 power 9 minus 137.84x equals 1.5x. Okay, so rearrange this plus 1.5, I get 139.34x equals 1.4749 times 10 power 9. So you can see the intermediate steps I use more SF. Okay, so I make a mistake here. This is not 10 power 9. This is 10 power 11. Okay, I copied wrongly. So same for here. Okay, so take that, divide by 139.34, and get x as 1.0548 times 2, 3, 4, 5, 6, 7, 8, 9 times 10 power 9 meters. Okay, so this is approximately, we follow 3SF from them, 1.06 times 10 power 9 meters. Okay, okay, next, part B. Hence, deduce the position on the line joining the centers at which the gravitational potential is maximum. Now, the place where the gravitational potential is maximum is also the same place. It will be the same location. Okay, because that's where the neutral point is. Okay, so the position POSITION is also 1.06 times 10 power 9 meters away from the center of mass of Jupiter. Mass of Jupiter. Now, what happens is that you need to explain why. Okay, so we can explain by that is the place at which gravitational potential is a maximum is at the neutral point. Okay, you could also use maths and explain. So you can say that V, if we do this, let's say V equals to negative. No, V is not negative. So it's like it's the gravitational field. Sorry, is equals to negative dV dr. And when V is maximum, dV dr is equals to 0. So G equals to 0 at the neutral point. We can use maths to explain this. Okay, last part. A rocket of mass m is launched on Ganymede in the direction away from Jupiter, as shown in the diagram. So by considering the total gravitational potential energy at the surface of Ganymede, calculate the escape velocity. Okay, so this is where the rocket is. So what happened is that from Jupiter, this is the distance plus the radius of Ganymede is a total distance. Okay, so we need to calculate the total gravitational potential energy. Total GPE of rocket equals to G mass of Jupiter over 1.07 times 10 power 9. That is you realize that is the distance here, plus the radius of Ganymede, which 2.64 times 10 power 6. Okay, so plus 2.64 times 10 power 6. It's not big, but you can still affect a little bit. Okay, with a negative sign here, plus the negative of G mass of Ganymede over just 2.64 times 10 power 6. Okay, so from here, we just need to use the GC. Okay, let me calculate it. Mm. So you get the mass of Jupiter, which is 1.9 times 10 power 27. 1.07 times 10 power 9 plus 2.64 times 10 power 6 plus then now the mass of Ganymede. 1.50 times 10 to the power of 23 divided by 2.64 times 10 power 6. Okay, we must remember to multiply by 6.67 times 10 power minus 11, which is the gravitational constant. So I get 1, 2, 3, 4, 5, 6, 7, 8. I get 1.2 negative 1.219 times 10 to the power of 8 joules. Okay, that's the GP of the rocket. Now, from surface to infinity, we always need to do this for work energy power. So from the surface to infinity, there is a gain in GPE equals to loss in KE. Okay, so loss in KE equals gain in GPE. Loss is initial minus final. So initial, to be more proper, just now it's not GP, it's gravitational potential because I didn't include the mass of the rocket here. Okay, forgot that. So it's this gravitational potential. So it's joules per kg. So now we put the mass of the rocket here. V square minus 0 square. Okay, loss is initial minus final. This is final minus initial, which is negative 1.219 times 10 power 8 multiplied by mass of rocket, which cancels out. Okay, so this will turn it positive. So V square equals to multiply by 2, 2.43 2.438, okay, times 10 to the power of 8, and we get our V square root it 15616, okay, which is approximately 1.56 times 10 to the power of 4 meters per second. Oops. Let's move it. Okay, so this is the escape velocity of the rocket.